welcome back to the fourth week of this course. So, as of now, we have talked about some of the historical perspective and all the way to this century when we have seen significant bioterrorism threats. And in the last week, we talked about one of the very first sensors, which is quartz crystal microbalance. So, one of the things which I desire to highlight from here onward, the modern instrumentation or detection tools which are presently being employed and in future they will come, they will be mostly combination of multiple tools. What really does that mean? Means, say for example, you are seeing something using microscope. So, you just get a morphological information. Now, you won't get a chemical information from that. For that, you need another set of tools. So, if your sample is limited, then you are always at a risk of losing information, right? Because if you use one sample for microscopy and you get another similar sample for spectroscopy, use another one for its physical properties, then it will be a cumbersome situation. But when we talk about bioterrorism or any agents like that, they remain in very trace amounts. So, whatever techniques we used, preferably, point 1, preferably they should be non-invasive. Secondly, you should have a detection assembly where the same sample could be utilized for both microscopy, spectroscopy, other physical parameters, and without breaking the system, you should be able to derive all the informations. Because when you are breaking the system, there are two things. Of course, you can gather more information, but you are also exposing yourself to the chance of contamination, right? So, what you will realize in this week, while we will be talking about next set of techniques which have been coupled with electrochemical systems, you will see how the modern instrumentation, detection, biosensing is much more multi-modular. In a way, in the same system, you can perform multiple activities. So, to start off with, so this is our lecture 16, we will start with the basics of atomic force microscopy, which is popularly known as AFM. AFM as a biosensing tools. What really AFM is? As the name says, atomic force microscopy. So, you are seeing things at the atomic level. How it is being done? You must have seen some of these images at some point or other. There are these images where you could see there are kind of dark patches, then you have lighter patches, and based on that people deduce what is the pattern on the substrate. So, before even we get into the details of what really AFM is, let us discuss in a simple way what really AFM looks like. So, say for example, you have a sample like this. This is your sample, and I am not mentioning the dimension or the scale at this point. For example, this consists of a lot of different kind of compounds. Now, if you, and it is distributed on the surface like this. If you have, say for example, you are walking on this street with a stick. So, as you move, your stick hits here, then as you move forward, your stick hits here, and you are climbing now, right? Your stick hits here, your then stick is now coming down likewise. Okay. you're realizing your stick is following imagine a blind person is walking with a stick and kind of trying to figure out how you're walking. That's exactly is the very closest analogy of what AFM is, AFM tip is all about. Say for example, instead of this stick, now I draw something like this. And now I replace this stick with a tip. And this tip, the end point, is at an atomic resolution. Now, what you are doing while you are walking, imagine you are being replaced by a motor which is moving which is allowing this pin to move like this. So, now this pin, now again let me draw the surface. Now, this pin is now moving under the influence of this motor. This motor is allowing it to move. So, it will move, it will trace it like this. Eventually, it will give you a profile. It will say, okay, here you have the height is like this, here you have lower height, here you have higher height, again lower height. There is a height, but this is not as high as the previous one. If I call this as T1 point, this is T2 point, then there is a T3 point, then there is a T4 point. So, you can say that T1 is slightly smaller than T2, while T2 is greater than T3. So, well, T3 is greater than T4, which is the fourth one, likewise. So, you can get a profile of the surface, and that's exactly is the very first application of AFM. It can give you a surface profile. So, say for example, if this surface would have been, now if this surface would have been something like this, and your tip would have been moving like this, and you would have seen no variation of contrast. Now, if you look at this image, now you kind of correlate it. Now, if you look at it, there are these depth, these are the depth profile, and you see lighter, it means it is shifting like this. And if you look at this graph, looks like this. So, there is a repetition, and this repetition brings something called order. And if you could correlate this order with some chemical structure, then you know you're hitting the bullseye. And this particular technique exactly goes down to that level. But having said this, let me come back to another situation. Say for example, when I say that these curves what you see are okay. Now imagine some of these are flexible. Means you have sit on a sofa. Once you sit on the sofa pushes back, right? And once you get up from the sofa again comes back to its original shape, right? Now, say for example, this surface has a tendency to fall back like this once it gets a pressure. So, if you are moving with this probe, the probe hits here, it may even be able to go further down. But then when it is doing so, there are two kind of informations which it could gather. One, and I am not getting into the how you are gathering information, I will come later into that. One, when you are hitting, so the probe is hitting a surface like this. Say for example, this part, this in my palm. So my palm collapses, right? It will collapse. You could see that. There is a dent which is happening, right? Now, whenever there is some such dent is happening, the tip experiences a vibration. It will start to vibrate like this because it is hitting on a surface when it is on a touching. Or you can do the other way. In order to remove that, what you can do is that you generate or create a tapping in the tip itself, and you know the tapping frequency. You know that it is tapping at a known frequency. Now, if you hit the surface, if there is a change in the tapping frequency, that means surface has a very characteristic feature, right? And similarly, if the tapping changes, so if it is a harder surface, then it will have a different kind of tapping frequency versus if it is a softer surface. Depending on the surface, nature of the surface, the tapping is going to change. So that brings us, as we will be proceeding, there are multiple ways this tip can be changed, or this tip conformation can be altered, because this tip conformation can bring a whole lot of independence and degree of freedom for the user while you are working with AFM. So, it is very important that you try to push your imagination to the maximum level what all it can do, because there are surfaces, then again there are molecules which can absorb vibration, because mind it, you have a tip going and it is hitting the atoms. So, it itself will create some kind of a disturbance in that. That may even create vibrations out there. Now, think of it. Now, here you have a surface, here you are tapping it with AFM, and on top of that, say for example, you have another microscopic view somewhere or other, if you could put it together, and underneath you have some kind of a spectroscopic setup. So, what it will do is, on one hand you will be doing AFM and you will get the image of the surface. There will be microscope which will do additional feature detection on the surface, and you have a spectroscope underneath which will allow to identify the different form, different kind of atoms which are present there. So, in a way, what you are trying to do, you are using and coupling AFM with multiple other systems in order to extract information from extremely minute samples. And that is why, as I was mentioning while I started this lecture, that most of the techniques which are currently underway are complementing each other in one single platform. So, we derive maximum amount of information from any given setup. Okay. So, with this I will give you some idea when I talked about peak force tapping. So, this is the kind of tapping I am talking about, and here you have the substrate and here you have the tip. So, areas what you can explore is atomic topography, nanomechanics, electromechanics, nanoelectronics, nanospectroscopy, nanoelectrochemistry. And all these techniques, when coupled together, is what will be the dream when you will have detection systems. So, even the smallest of the smallest sample will come under the scanner of these kind of probes. Now, why atomic force microscopy? Let's talk about it. Why AFM? Atomic force microscopy is generally used to capture 3D topographic images of a sample surface. As you must have already realized, when you are moving that tip like this, what you are getting is you are recreating the topography of it. If you go back, look at it. You are basically recreating a three-dimensional geometry of the whole surface, right? Today, it can be routinely achieve atomic resolution to identify monoatomic steps and ripples in the direction and resolve lattice orientation and surface defects in the plane. In addition to traditional contact and tapping modes, what I was mentioning you, novel modes have been developed to stably control ultra-low imaging force, thus preserving both AFM tip and fragile samples. So, you're realizing, as I mentioned, there you have the tapping mode, and we'll come to that. What is the tapping mode and what is the contact mode? These modes also allow precise local stress to be applied to samples for mechanical, electromechanical, and piezoelectrical studies, and we will come to that. What does that mean? When you are using the tip like this, you are tapping it in order to figure out that what kind of mechanical deformities you can do. You remember in the beginning I was telling you that you actually can tap the surface to figure out whether the surface deforms or does not deform. Based on that, there will be change in the vibration frequency of the tip itself, and based on that you can figure out what is the nature or what are the mechanical nature of the particular substrate. Okay. So, coming back on the slide, beyond topography and local forces control, advanced AFM modes allow researchers to capture image of modulus, adhesion, deformation, conductivity, surface potential permittivity, optical absorption, and reflection and electrochemistry. This information is generally captured through multimodal imaging at normal or high speed acquisition rate, which makes correlation among different properties possible. In addition, AFM works not only under ambient condition, but also in controlled environment, including liquid, varied temperature, dry box, and vacuum. All these capabilities contained within one single instrument make AFM a versatile platform for investigating highly multidisciplinary research. This is exactly what I was trying to explain to all of you, that today's AFM are exceptionally robust piece of instrumentation. Now, basic forms of AFM, as I was mentioning, let's explore that. In the most basic form, AFM involves scanning a sharp probe across a sample surface while capturing information about surface properties, right? As I mentioned, it has been used initially for surface profiling and scanning the surface. An AFM probe is composed of a substrate, a cantilever, and a sharp tip. So, it's mostly something like this, which is the cantilever part, and this is the sharp probe, right? The substrate is rectangular chip with sides measuring on the multimeter scale and serves as the connection point for the probe. The cantilever protrudes from the substrate, can be triangular, rectangular, or other forms. So, this shape can be manipulated and changed and measures in micrometer. The tip and the part that interact with the sample surface provides high resolution, is at the end of the cantilever and measures in nanometers. So, this is the point. The AFM probe is capable of high resolution imaging due to combination of efficient piezoelectric actuation. So, if you remember, when we talk about the QC and we talk about the piezoelectric process, here again we are getting back into the piezoelectricity that is used for precisely drive the tip of the sample, use the sharp tip with optimal mechanical properties and a fast feedback control loop for maintaining the user defined tip and special sample retraction. I'll come to that, and that is something like this. Say, for example, when you are shining a laser beam on the surface, this is the photodiode which is detecting. So, in that process, what you are trying to do, so here is the tip, right, and here is the surface. The force between the sample surface and tip. So, atomic force microscopy, the feedback system responsible for achievement of such high resolution is based precisely sensing the interaction between the tip and the sample using laser bouncing optical lever technique that utilizes fast position sensitive photodetector, which is the PSPD, which is present there. Now, coming back to the previous slide, okay. The piezoelectric actuators together with the feedback loop allow for the tip or sample movement control at a picometer scale. AFM probes with different chemical, geometrical, and mechanical properties are commercially available, each of which may provide different information depending on the interaction with the sample. Probes with normal end tip curvature radii of 1 to 2 nanometer are now also commercially available. So think of it, a tip of 1 nanometer. You technically can really get into the 20 to 30, or at least, at least 10 to 15 atomic resolution level. So that's the power of atomic force microscopy. And this is just the beginning. There are a lot of things which are now being added to it. One of the things which I did not say, for example, this laser, when you are shining the laser, if the laser passes through the tip itself, what will happen? This is another mode, and I'll come to that mode. What does that mean? Okay. So having said this, now we will wind up this part with all the different settings of which are available with AFM. So this is the basic setup of AFM, where you have the laser, you're shining the laser, you have the photo detector here, and here you have the tip, which can go all the way up to 1 nanometer, which are now commercially available, and it is moving across the sample. This is the basic setup. Setup B is the tip sample interaction for quantitative nanomechanical studies. We will come to that in the next class. Third thing, this is scattering, scanning, near field optical microscope, SNOM, and we will have few other modification to that, which is this one. And the third one, AFM based scanning electrochemical system, ACCM, where the insulated AFM serves as a nano electric probe, which is the third one. So overall, this is the whole aspect of AFM, which is at its most basic form. But from here, what we will do, we will talk about, say for example, this mode, what you see. This probe, either it could be static or it could be tapping. There are two things it can do. Or this will touch or / contact the surface versus non-contact. Okay. Third, you create disturbances on them, a known amount of disturbances, and see the change. Does it resonate at what frequency? We'll come to that, where we will talk about the resonance frequencies of these different kind of probes which are being used. So what we will do in the next class from here is we'll talk about the different kind of modifications which have been done with AFM and how this is completely revolutionizing our understanding of the molecular detection and the structure as a whole. Thank you.